Alright, this video is covering the subject of symbol rate mismatch. Okay, so the problem that we're looking at here is, let's suppose we have a nominal symbol rate. Okay, I'm going to give you an example with some numbers here in a second, but a nominal rate means this is the rate we're expecting, but we all realize that the actual rate, the actual transmission rate, might be different. So what happens if these are not the same? Okay, so how do we handle this situation? Okay, so one model that we could do is we could say, well, the symbol rate is going to be close to the nominal. All right, if it's not close, then there's pretty much no hope. But if it's close, then one model would be you take the symbol rate and you multiply by 1, either plus or minus epsilon, where epsilon is a small number, small but non-zero. Okay, so that's what we're going to do here. And the answer to what we do about it is I'm going to just show you an example of how you would solve this, and in practice, of course, there's lots of different potential solutions for symbol rate synchronization. Okay, so in this Matlab example, I'm coming up with just pulling parameters out of the air. The sampling rate is 1 megasample per second. The symbol rate will make that 150,000 symbols per second. Okay. All right. So if we take a look at the upsample factor m that we've looked at many times before, that's the sample rate divided by the symbol rate. In this case, we get 6 2/3 samples per symbol interval. Okay. So if we're just looking at an example like this. Let's say we had a 0.2% difference. That would make epsilon equal to 0.002. Okay, so we multiply f symbol we multiply the nominal rate by 1.002 to get the actual symbol rate. Okay, all right, so that would give us the upsample factor at the transmitter to be f sample over f sim transmit. Okay, and what we're seeing here is between the nominal we're having a delta m of minus 0.0133 samples per symbol interval. Okay, a small difference. All right, so one way to think of that is looking at the optimal downsampling time. We're going to sample t now as we loop through our dual loop clock recovery algorithm. Every k, we're going to get a new downsample time. Okay, so at the transmitter, the real upsample factor is mt. Okay, so you can expand mt into mt is equal to m plus delta m, all right, and then you distribute the k across, and we arrive at this expression. Okay, so with our dual loop clock recovery algorithm, we're going to have two different tau estimates. Okay, the first tau estimate is sort of I view this as the course adjustment. Okay, so it's trying to course, C-O-A-R-S-E. The course adjustment is trying to get in the ballpark of the right value of MT, all right? And so K times delta M, the tau 1 estimate is going to try to follow that, all right? But it's going to be a little bit off. It's going to be probably K delta M plus some DC offset, okay? So the tau 2 estimate could track any fractional component of the sampling time, tau, plus any error that shows up in T1. So I'm hesitant to say that tau 2 is tracking tau, because it's doing more than that. It's taking care of some fine adjustments between tau and also what happens within K delta M. All right, so we'll run some examples and take a look at this. All right, in the Matlab code that I'm going to show you, we are doing a dual loop clock recovery. And I realize when you look at that, it just looks like a bunch of lines of code. So I wanted to discuss sort of the big picture on what this algorithm is trying to accomplish. Okay, so in the big picture, x of n, these are samples of the waveform. Okay, this is at a sampling rate of fs, the sampling rate of the system. And coming out, we're going to have the down samples, all right? And so this is going to be at the downsampling rate. Okay, so f sample divided by m in this case. Okay, so to get this to work, we realized that we had to use the interp sync function to do resampling logic at the optimal downsampling times. Well, we don't know what the optimal downsampling time is, so we're trying to make an adjustment for that. So the resample logic includes the interpolated value at kt over m plus tau 1, but it also uses the plus delta and minus delta options on this to estimate the derivative. So I'm hiding all that inside the blue box, but you take all these, it takes 3 interpolation values in this step, 3 here, and these get fed into the update equation for tau 1. All right, so every time you go through the loop, you've updated tau 1, you feed that back in through in here and back down into the second update loop. Okay, the tau 2 loop, I think of that as the fine adjustment loop. Okay, so you take the logic from tau 1 and then you also update tau 2. Combine those together and out comes the downsampled signal values that should give you the soft decision diagram. Okay, so next up, let's go over this in Matlab.
Okay, let's go over the Matlab code for this example where we have a symbol transmission rate mismatch between the nominal rate and the actual rate used by the transmitter. Okay, so I do these over and over, and I'm hoping the repetition will help it sink in. So let's just go over everything real quickly. We first generate a sequence of symbols. All right, I assign a sampling rate to this. We're going to assume we're sampling at 1 megasample per second, and as we discussed in the setup to this example, our symbol rate is going to be 150,000 symbols per second. So that gives us a nominal. Okay, remember, m is the nominal sampling rate. Upsample rate. And when you run the Matlab code, you'll find that m is 6 2/3. All right. So I made a 2% error in the transmission rate between the nominal rate and the symbol rate used at the transmitter. Okay, so that gives us an NT value. All right, and if you check on this, you go to the Matlab window here. I've already run this code, so if you check on this, you'll see just a second. Okay, you'll see that MT is 6.6534, and so we can look at the difference between M minus MT, and you get the 0.0133 difference. I think in my notes I did the opposite direction, MT minus M. And so that jives with what we've already set up for this example. Okay, so from here, I'm now going to simulate the system, all right? And that's why we needed this improved model so that we could do this kind of simulation. And so to get this, we need the upsample and downsample factor that would let us simulate this particular symbol rate. Okay, so our symbol rate is going to be 150,300 symbols per second instead of the nominal 150,000 symbols per second. Okay, so this RAT function, ratio function, tells us let's use an M of 173 to upsample, and then we downsample by 26, and this will give us the overall model for our communication system. Okay, so we use square root raised cosine pulses. We convolve that with the upsampled, we're upsampling by cap m here, right? Cap m comes from this ratio function. We upsample, we downsample by n. We have to scale this. This explains why. We probably talked about that a little bit. And once we do that, we get the proper signal that we can send over the communications channel. All right, the next thing though that I wanted to point out is once you have the signal, you would do receive filtering. And if you'll notice here in the square root raised cosine pulse, when I did the receive filter, I used the nominal rate. Okay, so if you think about it, at the receiver, I don't know that the rate is off at that point. Okay, so I use the nominal symbol rate to get the matched filter to do the receive filtering, not FS-sim T. I use F-sim here. Okay. All right. So from here, let's move into the algorithm. Okay. For the algorithm, we also use the nominal rate. It wouldn't be fair to use knowledge of the error, right? So we assume a nominal rate, and this algorithm processes things based on that nominal rate. And of course, what we're supposed to do is undo any distortions that would come from a mismatch. Okay, so these are the normal things. This is the that blue block that I was telling you about, where you do the logic to do the interpolation. This is the update equation for the blue block. Okay, so I get a new tau1 and I feed that into the next level. All right, so this is the orange block where I'm doing the resampling of the signal to get what I need for the update equation for the orange block. All right, and I feed all that in, and this gives me the update. All right, so T now is going to be updated at every step to give me the optimal downsampling times. Okay, so notice here, I say T now. T now down here is just keeping track of the, the step sizes. Here's the optimal sampling time. It's going to be T now plus tau1 plus tau2. We interpolate that and store that interpolated value in XS. Okay, so this is the output showing up of that block diagram that I had previously in this video. This would be the X of K signal coming back out. It gives you the soft decision diagram. Okay, so we run this, and the eye is open. It's taking care of this, but you can look at this offset estimate. It's this K times delta M that I was talking about before. All right, so we're trying to keep track of this mismatch, and then you can see some fine adjustments that look a little noisy. We have a pretty high value of mu1 and mu2 set up for this example so that it will track quickly. But you can see the soft decision diagram, the eye is pretty wide open here, and this is all looking good. All right, the next thing I wanted to show you is, if in fact this thing is tracking the delta M, the difference between the upsample factor that's nominal and MT, okay? If in fact it's tracking that, we should be able to look at that slope, okay? So here's how I do that. I can calculate this by calculating some points on the graph, and I'm going to use G input to do that. That's the Matlab trick. So G input means I'm taking inputs from the mouse clicks on a figure. Okay, so I hit return here, and let me grab, I'm going to click once here, and I'm going to click once here, and that gives me two different values of X and Y. All right, so I can calculate that slope. Okay, so I can call that delta M, dm. All right, that would be YY of 2 minus YY of 1, the difference between the y values divided by xx of 2 minus xx of 1. The indices indicate which click I use. So second click minus first click on the top, second click minus first click on the bottom, hit return, and I get minus 0.0128, which is not as close as I expected, but it is reasonably close to showing that it's tracking this difference. I'll have to look into that a little more. Okay, so that basically wraps this up on clock synchronization. As I mentioned when we talked over the Zoom meeting, the next step up is looking at channel equalization. Okay, a quick follow-up to this, looking at the slope of this tau 1 offset. Remember, I was a little surprised that the slope didn't match better with the difference that we calculated delta m. So if we do mt minus m, we got minus 0.0133. And if I looked at the m value that I had by calculating the slope from the tau estimates, they're pretty close, but they're not exactly right. Okay. And so as I looked into this, I remembered that we are simulating this based on an upsample factor of m and a downsample factor of n. Okay, and it's supposed to be that m over n gives you, mt, but it's not exact, right? Remember, if I put that tolerance in there so that we wouldn't end up with really long simulation times. So if I take a look at the real simulated system, okay, the MT that we actually used, so I'll call it MT actual, is going to be M over N. Okay, so if I take M minus MT actual, I get the value that's the slope coming from this tau estimate. Okay, so that explains that slight mismatch. It's because our model wasn't perfect for simulating the example that we formulated in class. All right, so hopefully that helps. Again, the next step is on to channel equalization.